All right, what's up everybody? Today we have a mouthful. So we're talking about second order linear constant coefficient homogeneous ODEs. What in the world does that even mean? Well, it means that the ODEs look like this. They look like some AY double prime plus BY prime plus CY equals 0, okay, where the A, B, and C are just real numbers. A is non-zero, okay? Because if A were 0, then there is no second order here. I'm talking about first order if A is 0. Okay, A, B, and C are just constants, so that's what this notation means. And then the homogeneous just means that it's equal to 0 on the right-hand side. Okay, there's no term involving the independent variable, which let's say the dependent is y, so independent is say x or t or whatever. So there's no function solely of the independent variable on the right-hand side, not attached to y. Okay. So that's what the ODEs look like, and that's its name. Second order linear constant coefficient homogeneous ODEs, which is a mouthful. And the question we want to ask are, what do the solutions to this look like, and how do I actually find them? Okay? So the idea, remember, a solution is just an assignment of y, such that when I plug it in here, I get equality, like I actually get equals 0. And so you start looking through functions in your head, and you're like, well, what if I tried sine or cosine? It's like, well, if y were sine, then its derivative is cosine, and then the derivative of that's negative sine, so it's like, how would I eliminate the cosine here? So you're like, I don't really understand how I could cancel that just with constant coefficients. So what you realize is like the function that seems to make the most sense is the following, okay? So you say that y equals e to the r times t is a solution, okay? Well, that's if and only if what? Well, y equals e to the rt, okay, so then what's its, I'm going to need to compute its derivative. So y prime is r e to the rt, and then y double prime equals r squared e to the rt. And so this is why this is kind of like, this actually makes sense. Because look, when I plug in y prime, y double prime, and y into this, it's the same function. It's just scalar multiples of each other, depending on what r is. But it's just the same function, and so then I have a shot of choosing constants a, b, and c such that I get 0. Okay? So y equals e to the rt is a solution if and only if what? Okay, well, let's substitute those in. I'm going to get ar squared e to the rt. Okay, that's plugging in y double prime. And then plus by prime, so plus br e to the rt plus c e to the rt equals 0. Well, what's beautiful there is that everything has an e to the rt, so I can factor that out. So that's if and only if I have ar squared plus br plus c e to the rt equals 0. Okay? But that's if and only if what? Well, that's if and only if I have the product of two things is equal to 0, and they're real numbers, and therefore, since e to the rt is never 0, I can just divide by it. That's telling me ar squared plus br plus c equals 0. Okay? Now this thing is so special, this has a name. Okay, we call it the characteristic equation associated to the ODE. Okay, so this is the characteristic equation. And it gives you a way of finding solutions to your ODE, because then what we're really saying is that e to the rt is a solution provided that r satisfies this quadratic equation. Well, the quadratic equation boils down to having roots equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Those are what the roots are going to be, and they come in three types. Well, if b squared minus 4ac, which is the discriminant of this quadratic, if b squared minus 4ac is positive, I'm going to get two distinct roots. If b squared minus 4ac is 0, I get one root that repeats twice. And then if b squared minus 4ac is negative, I'm going to get complex conjugate roots. Okay, so in another video, I'll explain the different types of solutions for each of these, and we'll walk through what the corresponding solutions are going to be, if they're distinct real, repeated real, or complex conjugates. Okay, but this is just introducing how do we actually find solutions y equals e to the rt for second order linear constant coefficient homogeneous ODEs. It boils down to solving this quadratic equation. So there you have it. Now you know how to solve second order linear constant coefficient homogeneous ODEs, if only saying the name was as easy as finding their roots.